All right. Thank you, Vivian and Emma, for that wonderful talk and the introduction of Snoopy and all his friends. So let me see. If you have questions, please, again, raise your hand and we will promote you so that you can ask it live. Otherwise, post it on Slack. And just to get things started, one of the things I really like about your paper is this lower bound, or not lower bound, but this bound that you found to actually pad the number of requests. And one of the things I keep going back to is, are there other applications that you've thought about that might leverage this bound? Because this seems to be orthogonal to Snoopy a little bit.
So that's a great question. So our bound, so I don't think I have any concrete examples of applications where this is useful, but I think that what's really unique about this bound is that in a lot of prior work, the probability of overflow often depends on application parameters. It's like the number of balls or the number of bins. Whereas in Snoopy, the probability of overflow is independent of these parameters. And so that allows us to get this probability being negligible in a security parameter. So I think that this is really useful for applications that are really focused on security, where you need to get this negligible, this negligible probability of overflow, and where maybe you don't have a lot of control over certain application parameters, where they depend on parameters that you can't necessarily control or fix, or maybe it's helpful to have parameters set in a case where existing bounds don't actually give you the probability that you would like.
Cool. And I think Yiping has a question. Yiping, go ahead, ask the question.
Yeah, so I have a question about the load balancer. As if I understood correctly, I saw in the paper that the batch size is determined under the assumption that the real requests are randomly distributed over the sub-ORAPs. So if the distribution of requests is really unbalanced, how will the batch size be determined?
Yeah, so that's a great question. And essentially you're asking like whether we can handle skewed workloads, right? And in order to handle skewed workloads, we actually have this Oblivious deduplication algorithm at the load balancer. So what ends up happening is that if you say all of your clients are requesting the COVID object, what happens at the load balancer is that you transform that batch of requests into one request for the COVID object and then n-1 random requests. So that when you feed like your actual request batch into this bound, you do have like n randomly distributed requests.
I see, thanks.
Okay, and I believe Edward had a question next, if you want to ask it.
Yeah, thanks. So great work. And I just wondered if you could explain, you said at the beginning, we have to assume that clients trust each other. Why is that? Because I didn't actually see that came up in your explanation of how it worked.
Yes, that's a good question. So we talk about this a little bit in detail in the paper. One thing that's a little bit subtle here is that if you have clients that don't necessarily trust each other, and you want to give permission to some clients to read some objects and other clients to read other objects, you essentially need to implement some form of access control. The trick with this access control is, let's say I want to know, does Alice have permission to read, object 1? If I just do a lookup in my access control matrix on a hardware enclave, where I access in this access control matrix is actually going to leak which object I'm which object I'm accessing. So you need to do this lookup in the access control matrix obliviously as well. This is pretty straightforward. We talk about this in the appendix of the full version. Basically, you just run Snoopy recursively is one straightforward way to do this. Also, if you're not dealing with access control, this can be done a little more straightforwardly. If clients maybe don't necessarily trust each other, but they all have access to the same set of objects, like if you're just looking at things that are all public, like in a public key transparency log, for example. But we just make that assumption for the presentation just to simplify things. But we do in the paper discuss both the case where you deal with access control and the case where clients don't necessarily trust each other, but all have read access to the same set of objects.
Okay, yeah, that makes sense. I was wondering if clients needed to communicate with each other at all, like to coordinate their requests, but it's really just a matter of enforcing access control would
exactly. So clients can make arbitrary requests. We assume actually in our security definition that the attacker can choose the requests that the clients are making. So there really isn't any need for coordination or making sure that their requests are sort of coordinated amongst each other in some way. but it's just the subtlety with how you do access control. It's the only reason that we just defer some of like the slightly harder. It just becomes slightly messier. That's really it.
Okay, yeah, that makes sense. Great.
Awesome, thank you. I think Bogdan had a question, which is also very similar to a question that Jack asked in Slack. So you get 2 for 1. Just like the talk, we get 2 for 1. Wonderful. Go ahead, Bogdan.
Hey, everybody, can you hear me? Yeah, awesome. So great work, and I really like the presentation format. Yeah, so sorry, Jack. I think Jack also asked a similar question, and maybe this is orthogonal to the design of Snoopy, but I was wondering, how does it handle node crashes and fault tolerance in general, if at all, or if you think to extend it to handle that?
Yeah. So this is a great question. So I'll answer both like the fault tolerance question and also try to cover Jack's question in the chat as well, since they're really related. So we do talk about this at a high level in the paper. It is sort of an orthogonal question a little bit, but it also is relevant because you're trying to build, a system that scales. Obviously, at some point you're going to need to deal with node crashes. So dealing with node crashes at the load balancer is pretty straightforward because the load balancer is just managing really just short-term state. So the only really like long-term state that you have to worry about, we shard objects across sub-ORMs using a keyed hash function, so the key for the hash function, as well as any system configuration information. So if the load balancer fails in the middle of processing a particular batch, we just abort that entire batch. To get back to Jack's question, just in the middle of this, because we abort the entire batch, this makes sure that if some clients need to retry, it makes sure that it ensures that we're never in the position where some clients need to retry from a particular batch and other clients don't need to retry. So now getting to this question of sub-ORM failures. So the sub-ORM does store long-term state that we need to make sure if a sub-ORM fails, we could actually be in trouble since we lose information. So here you can actually just use standard replication techniques in a pretty straightforward way. Just replicate stuff across the sub-ORM, and all the sub-ORMs execute the set of requests. Just make sure that all of them have completed before you send back to the client that you're actually done. There are some interesting subtleties when you're dealing with replication and enclaves, because enclaves can be rolled back. And so we talk a little bit in the paper at a high level about how to compose traditional replication techniques with some of these rollback prevention techniques. There's some systems like ROTE, there's this XGX monotonic counter. Basically, you need to make sure that you're replicating to enough replicas that enough will still be online and enough won't actually be rolled back. So there's some interesting questions there as well. But anyway, sorry, just to make sure I've actually also answered Jack's question. So basically, if a client repeats requests because of the security from ORAM, that's not going to reveal anything. And because either the whole batch succeeds or the whole batch fails, if a particular client retries it, you're never going to be in the position where a client participating in this batch, where one client's going to retry the request and another won't. So that won't leak anything. I hope that answered both.
Yeah, thanks. Awesome. Thank you.
All right. So Edward, so sorry, please ask your question in Slack, and then we will we'll cover this so we can move on to the next talk. Thank you, Vivian and Emma, for presenting Snoopy. The only comment I have is that the acronym was a little bit, or like the it was a little bit of a stretch, but otherwise it was great. So the next talk we have is, I think I'm going to pronounce it correctly. I think it's Kios. It was a hard word to pronounce, and it's going to be presented by Ishtiaq. And the goal is how to privately find.
That's great talk, actually. Sounds very interesting. So we already have one question from the Slack thread. So I posted here, both the M and Vivian. You can take a look. The question made by Feng from Shanghai Jiao Tong University, and the question is, as you have mentioned, the existing ORM algorithms use remapping to hide the access pattern, but they are not non-scalable. In contrast, the Snoopy used batching and adding dummy requested to all this sub-ORM with some optimization. So is there any trade-off between these two methods? Like the Snoopy may sacrifice the bandwidth if there are a large number of the sub-ORM. Yeah, please go ahead.
Yeah, thanks so much. This is a great question. So basically asking about the trade-off between existing ORMs that use remapping and systems like Snoopy that are able to scale out. So existing systems are really good in the case where you really care about latency and communication. Snoopy is really designed for the high throughput regime where there are a lot of requests, a lot of concurrent requests, and you need to scale out to handle a really high volume of requests. So this is really the regime that Snoopy is designed for. If you're in a case where you can handle it with just a single server and you really care about latency, Snoopy might not be the best for that particular setting. Also, just to clarify from the question, Snoopy allows you to scale out to multiple machines. So you can't really imagine, so there's not really an existing system that allows you to sort of scale compute out in the same way without a bottleneck. So there's not really a concern about Snoopy sacrificing bandwidth in that setting. Yeah, great question.
Okay, sounds good. So there is another question. So let me first post it here. Okay, this question from this Zhengyu Park. I don't know how to pronounce the name of the university. The question is that I don't have background on this, but what could be the concrete example that's used? The people use this Oblivious storage. So is it something like the Apple Health stuff? Yeah, just about the use cases.
Yeah, so in terms of use cases, you can think of really like anytime you want to outsource storage to an untrusted server like the cloud, you can encrypt that information and that gives you like a layer of confidentiality, right? But it turns out that the rate of access that you like, say you access like this object A, maybe the server doesn't know the contents of it, but if you're accessing it like once a month, an adversary could infer some information. So like a concrete example of this would be like a doctor, if they're accessing say like cancer treatment records, based on the frequency that they access, you could even infer something about the type of cancer that the patient has. So that could be it. Yeah, but great question.
Okay, so we have a question from audience. Jiang Jianyu, please go ahead.
Hi, great talk, and I'm Jianyu from Hong Kong U. So I have two questions. The first one is, I wonder what is the threat model of the Snoopy, because I see that you want to hide access patterns in SGX enclaves, and as in SGX enclave there's different, it leaks access pattern in different granularity, such as page or catch sets or etc. And it seems to me that you are using Oblivious algorithm to pad the things to sort it, and I'm wondering if it would be overkill to use such a method instead of using like page level Oblivious or catch sets level Oblivious algorithm. Yeah, and the second question is, will the load balancer lead some statistic of the batch of the request? Because for example, if all the users are accessing the same keyword and values, then it seems that it would like generate less requests to the sub-ORMs. Thanks.
Yeah. So these are both great questions. So for the first question about building Oblivious, if I'm understanding it correctly, is about building basically Oblivious storage on top of hardware enclaves, where these enclaves are susceptible to these side channel attacks. So the threat model that we're really considering here is we have an attacker that can view both network communication patterns, so it can see where packets are being sent, the timing and how large these packets are, but not the contents. And the attacker, sort of getting to your point, is also able to see memory access patterns inside the enclave. So it can't see the contents of the enclave, but it can see what addresses are written to and read from. And so we talk in the short version of the video a little bit about how we construct these batches so the structure is oblivious. But we also talk in the paper, didn't have time in the 10-minute version of the talk. We also talk in the paper about how we generate these batches obliviously. So how we construct these batches and how we route individual requests to sub-ORMs is also performed obliviously, so that if an attacker can view memory access patterns, they're not able to infer anything about, for example, how requests are being deduplicated, the relationship between them, which sub-ORM they map to. And we also make sure that they're processed obliviously at these sub-ORMs as well. And then, sorry, really quickly, remind me the second part of your question.
Let me add something to the threat model question first. So my question is, so if in XGX it will leak some side channels and leaks the page level or catch set level access pattern. So I mean, would it be more efficient to use an algorithm that hides the page level, hide the page level access pattern instead of using a completely oblivious access to all the memory addresses?
Got it. Yeah. So we're really focused on building specifically for an abstract enclave model, where the attacker can view memory access patterns at sort of any granularity. And so if you have an enclave that only does provide obliviousness at, for example, like the page level, then maybe there's some things you can do at the implementation level to make the implementation more efficient. I don't think, just thinking, not thinking super deeply about this, I don't think the overall design of Snoopy would change very much, but there's probably some things you could do at the implementation level to speed things up if you knew that the enclave provided slightly stronger guarantees. But we're really looking at designing for this sort of more abstract enclave model that so you can more easily generalize to other enclaves where you have this stronger threat model.
Okay, got it.
Yeah, great question. And Vivian, did you want to take the second part?
Yeah. So to answer your second question, I think you were asking at the load balancer, if you have a skewed workload where like every client is requesting the same object, you might be seeing like less requests leaving the load balancer. So during the load balancer stage, like what we're actually doing is this oblivious deduplication algorithm, but we're not removing the duplicates, we're replacing them with different requests. So if you're given like a set of n requests to the same object, the load balancer ends up producing a batch that has one request to that object, and then n minus one requests to random objects. These are kind of like dummy objects, so that at the end you're left with like a set of n like randomly distributed distinct requests.
I mean, so when all clients are accessing the same objects.
Hi, Jay.
Okay.
Hey, sorry, I want to interrupt you because I want to give the chance to other guy. Okay. Maybe we can put it offline, right?
Yeah.
Okay. So what last question actually made by both Chao Yi and also the Min Yu from Shanghai Jiaotong University. They're curious about the crash recovery about this object store, right? So can this sub-ORM can tolerate the crashes, survive from crashes, and also where this crash is reveal any confidential information? Go ahead.
Yeah, so this is a great question. So we talk about fault tolerance a little bit in the paper, a little bit orthogonal, but because we're building, an oblivious object store that we want to scale out, this does become important. So talk about fault tolerance at a high level. So the load balancer really doesn't carry any long-term state. It just carries state for a particular batch. The only long-term state that it really has is a key for the hash function that's going to distribute the objects, and then system configuration information. So if the load balancer crashes, we can simply abort the entire batch and not send anything back to the client. So the client won't learn anything about what maybe has finished or what hasn't finished. Just all the clients will need to retry their requests. Now the sub-ORM does actually manage some long-term state, so we do need to be worried about what happens if a sub-ORM fails. To handle sub-ORM failures, we can use pretty standard replication techniques. So we can just replicate, we can just send the batch to all the sub-ORMs in this replica group. They'll execute things and keep copies. When they're all finished, only then will we tell the load balancer that we finished, and it can send the responses back to the clients. There is some slightly interesting questions that come up when you want to do this with enclaves and you're worried about rollback attacks. So we talk a little bit in the paper about how you can compose solutions for fault tolerance with protection against rollbacks. So solutions like ROAD or like the SGX monotonic counter. Basically, the short story is you need to make sure that you need to have that you have enough replicas that you can both fail and those replicas can be rolled back and you still have a good replica around. If I didn't get into any of the details people are curious about fault tolerance, I'm also happy to answer those via Slack since I know we're probably running out of time, but yeah, feel free to ask in Slack.
Okay, great. I think you had the question very well. Since we still have some pending questions on Slack, but we do not have time, right? Anne and Vivian, please go ahead to go back to the Slack thread and answer questions. And all the audience, if you have anything you want to ask, you can also do this offline. We need to move to the third one. Thank you both. Great talk.
Yeah, thanks for the questions.
Thank you.
Hey, okay. So the third talk will be given by